All right, so let's wrap up these slides then. So down we go. We were talking about loops last time, while loops and for loops. The next logical place to talk about and to go is functions. So let's make some functions that do some cool things. My best idea is let's do this cryptography function that is super simple, the Caesar cipher, if you remember that, ROT13 for short. It rotates every character of the alphabet by 13, right? So B becomes O, and O also becomes B because it wraps around. So it's like encoding some secret message like hello, it turns into Uryib. And then when you do it again, it goes right back to what it was. So that's like, it's its own inverse, which is cool. But let's make a function called ROT13, because that's the name of the encryption scheme, that takes like a string. We give it a string, it gives us, like we give it hello, it gives us a string Uryib back. How about that? That'll be nice. We'll end up making two functions, though, and I'll talk about that after we talk about functions. So this is the last page of the cheat sheet that I made for you. You get that from like last lecture's slides page. So to make a function, you have to define it with the def. Say def, the name of the function, and then you want to like pretend how you're going to call it. So figure out how many parameters you need to match how many arguments you're going to give when you call it. So you can give as many as you want between parentheses, comma separated. Those are the things that your function gets every time it's called. These are just names, variable names. And then you do a little colon, and yeah, in comes the body right after that. So some functions, they're just meant to be called in a line by themselves, and then some return something, meant to be used in a larger context. Remember the difference. So the ones that we're going to write are going to return stuff. And then, yeah, when you're ready to call your function, you say its name, and you give as many arguments as there are parameters, and those get passed on. The argument 1 gets placed into param 1, argument 2 gets placed into param 2. And essentially what happens when you say it like this, it's going to go jump to the body of the function, having set all the parameters to the arguments that you passed. Okay? That's what happens when you call a function, and if it gives something back, you better use it or save it for later. So maybe assign it to a result variable if it's something large that you need. So yeah, if it returns something, you can't just call it on a line by itself. Otherwise, that would have been useless. So those are functions. Let's make our own now. Let's make a function that takes a string and gives back the encrypted string. And then we're going to notice that it would be nice to also have a function that encrypts a single character of that string, because then we can just loop through all the characters. And I will show you my idea that involves two lists of characters, two strings, to do the encryption. So let me open up idle and show you what I'm thinking about. I'll make a new file for today, and this one is for encryption, so I'll call it rot13.py, and I'll save it in a folder for today, and I assume it's lecture 31. Let's confirm that. Yeah, so lecture 31 folder it is. And so rot13.py, here's kind of what I want to be able to do. Like I'd like to get a string from the user, or even like we can just hard code it if we want to right now. Like I want the user to be able to give me a string that's in all caps, like hello, and then we're going to write a function that like encrypts that string. So we can say rot13 on it, and it should give me back the Uryib, and I can just like print that out. That's how I'd like to use my function. Okay, and if you think about it, it's kind of a two-step process. First, you want to go through the entire string as you're encrypting it, right? And you want to like run this encryption on each character. So I think it would be nice to make two functions. One that works on entire strings, rot13 underscore string, let's say, and then one that works on individual characters to like take one character and encrypt it. And so it's a nice separation of concerns, I think. Let's do rot13 string. It takes a string, it's your text, and it does some fun stuff. And then I'll also, I want to also assume the existence of a rot13 on a single character. How do I encrypt a single character? And I'll use that in this bigger one. So if somebody gives me a whole string, what's my process? I kind of just need to like go through the string and build up the encrypted one. Does that make sense? Go through each character of this text and encrypt each character. So here's the idea. Like, I'm going to build up an encrypted string. I'll start it at emptiness. It has no characters in it. I want to go through each character of text and place the next character in its encrypted form into this encrypted string. So I'll do my fun do all my work, and eventually the answer will be an encrypted string. Return in, I can't spell encrypt, I guess, encrypted string. So that's the goal, to fill this with the encrypted version of this text string, like hello. Turn it into Uryib and return Uryib. Okay, so yeah, what I want to do is go through every character in text and encrypt it. And a cool thing that you can do is use a for loop over every character of a string. You can say, for every character, call it C in text. Just like if it were a list, you can treat every string as a list of characters, which is nice. And here I am going through each individual character, calling it C. What I'd like to do to that character is encrypt it. Encrypted character. This is where my encrypt a single character function will come into play. Let's call that 13 on the character C. It'll just run this code, give me back the encrypted form of that one character. And now, like, I had the H, C was my H, I just made a U out of it. It just gave me back the U, and I want to add that to the next character in my string. So I want to add that to the end of my string. Encrypted string equals what it was, all the characters. Maybe we're on the last character. Maybe we have we encrypted all of the HELL into URYY, and now we're working on the O, and we just got B back. We want to add that B to the end of this existing encrypted string. So take what was there and add that new encrypted character to the end of it. Does that make sense? So if only I had this function, and it did that, and it encrypted a single character, then I would be in business. Okay? So let's make that function, because this will be like the harder one, I would say. So here's my strategy. I think, like, somebody's going to give me a character, and I need to, like, if it's an A, I need to give back an N. If it's a B, I need to give back an O. If it's a C, I need to give back a P. I think the best way to do it would be to make two lists of characters, so just two strings called just characters in alphabetical order, and then encrypted characters, because watch what would happen if I were to do that. Here's like a string of every character in the alphabet: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And then I would like to, in each place, because you can use a string, and you can go to a place in a string, like here's my hello. You can treat it like a list, like go to character at index 1 of hello. You can do that. So that's what I'm going to try to do here. So encrypted characters. What's the encrypted version of A for ROT 13? It's N, then it's O, then it's P. It goes in order, and it wraps around. So N, O, P, Q, R, S, T, U, V, W, X, Y, Z, A, B, C, D, E, F, G, H, I, J, K, L, M. I think that worked out. So here's the secret. Like here, somebody gives me C, like somebody gave me H. What I'll do is I'll go find where H is in this normal alphabetic string. Find the H, figure out what index it was living at, and I'll go to that same exact index in encrypted chars. See that? That'll tell me the encrypted form of that one. That's what I want. That's the secret. That's one way to do it, at least. I'll find the index of C in the chars string by figuring out where that C lived. So I'll search through every possible index from A to Z, 0 to 25, I guess, because there's 26 characters. I'll go through every index, starting at index 0, and I'll go looking for that index of the character. Right now I don't have it, so I'll just say -1 to mean I don't have it yet. Make it start at something. But while I is less than the length of chars, go through every possible character, goes through index, because the length is 26, right? There's 26 letters in the alphabet. So while I is less than 26, so it goes up to 25, which is the index of Z, I'd like to look at that current index, chars of I, and see if it's equal to the character I see right now. Maybe it's the H. If it is, I was its index. And I'm going to go to that same I in encrypted chars. That'll give me the U from the H. Do you see that? This is a little complicated, but it's a good one to study. If chars of I, that's the character I'm looking at in my index I right now, is equal to that C I'm looking for, then the index of the character I'm looking for is I. And just like advance I equals I plus 1. Look through everybody. Eventually, you're going to set index of char to the one you saw, one way or another. You could break out of the loop. I showed you that before, but we'll just let it go through. And now, by the time this loop is done, I know the index of the character C, maybe it was H, in chars. And what I'll do is I'll go to that same index in encrypted chars, and that's my answer. That'll be the encrypted form. Go to that same index in encrypted chars. And I'll return encrypted chars at that index of char, whatever it was. And that'll, like, if I found that it was this index, go to that same index in encrypted chars, give back the U. And for each character, I'm doing that in my original string. And you see how that's going to eventually build up the encrypted form of the string. That's so cool. So I run that. I do, in fact, get my uryb. Are there any questions about how that's working? These two functions are playing together nicely. That's pretty nice. So that's a good one to study, I would say. Let's also remember how to use libraries. So let's start with the random library. That's a fun one. We'll import the random library. That's what you say to get it. And then what do you get access to when you import the random library? Python random. You can always look it up. The ones that we were using most often, randint, random.randint gives you a random number between a range of numbers. Then also, I think I showed you random.uniform as well to get a random number with decimal places, random floating point number between those two, between that range. So those are the things we care about. But let's use randomness to do some fun stuff. Let's use the turtle library too. So let's make, for my first example, let's do a random like Etch-a-Sketch program. You know what an Etch-a-Sketch is, right? You turn the little knobs and like you can go left, right, up, and down. And you make pretty pictures. If you turn them both at the same time, you can get curves made. That's pretty cool. Let's make that kind of program in TurtleLand. Let's just say, hey Turtle, go forward a random amount and then turn a random degree. Boop. And then go forward another random amount. Just like keep playing that game. Keep doing that forever and ever and ever. And it'll make some weird random drawing. Won't that be fun? So let's have the turtle draw a bunch of random lines and turn in random directions. Probably multiples of 90 would be best. And we'll eventually want to like stop the drawing. Let's say that we'll stop the drawing when the turtle goes outside of the range of like the inner 600 by 600 square. It's really a square, isn't it? Centered at 0, 0. So like if his x is, but like we want to keep the x between like negative 300 and positive 300. Same for y. If it ever leaves that bound, then we're going to stop drawing maybe. I think that would work. So yeah, let's use the random library and the turtle library to draw some stuff, like a random Etch-a-Sketch drawing. I'll call this etch-a-sketch.py. And yeah, let's import turtle, import random, and I always want my turtle to look like a turtle. Can't forget that. And then let's just say while true to start. I just want to, like, until the end of time, we can fix this later. We want the turtle to go forward by a random amount within some range, and then also turn by a random multiple of 90 degrees. Does that make sense? That'll work. Let's do that. And so, how do you go forward by a random amount? It's like turtle.forward in your current direction by some random number here, and we can use random.randint to get a random number between a range. What should our range be? Let's be like, I don't know, really short lines, 10 units, to even bigger lines like 50 units. That'll be a good one. And then let's turn by a random multiple of 90 degrees. It doesn't actually matter if you say turtle.left or turtle.right, as long as you cover every one of the 360 degrees. Doesn't matter how you get at it, but turn left by some random multiple of 90. 90 times random.rand int 0, 3. Okay, so that'll be that. Well, let's watch this work. So just like go forward forever, repeated. Go forward by a random amount, Mr. Turtle, and then turn left. Could as easily have been right by a random multiple of 90 degrees, and we have them all covered here. 0 times 90 all the way to 3 times 90. Those are all the options, right? 0 through 270, where 0 is the same as 360. Just don't go anywhere. Whee, so there he goes. He's moving around. And eventually, through the power of randomness, he will make his way outside of the screen. And we'd like to just stop him if he ever goes outside of the screen like that. So instead of getting this weird red text, let's just not make it an infinite loop. Let's keep track of where the turtle is and like make sure his x's and y's are within this range. All right? That'll keep him in the center of a 600 by 600 square. I think that would be nice. So how do we get the x and y coordinates of this turtle? There is a function that tells you where the turtle's position is. You can say turtle.position, turtle.pause, and you get a tuple back. Remember that? Where index 0 is the x position, index 1 is the y position. You could also just say turtle.xcore. That gives you back just the x coordinate of the turtle. Or turtle.ycore. That gives you back just the y coordinate of the turtle. I think those will be useful. So let's do that. So while the x coordinate and the y coordinate of the turtle are within this negative 300 to positive 300 range. So while like turtle.xcore is less than or equal to 300, and then you can do the cool math kind of, you can do this exact thing. You can say this exactly in Python, like negative 300 is less than or equal to turtle.xcore is less than positive 300. That's pretty nice. So like that gives you those checks all at once. Like, well, that's true, and also the same thing is true about the y coordinate. And the y coordinate is also within that range. And I think we can also make the turtle faster. Let's say turtle.speed fastest. We don't have all day. I'm trying to review stuff. And so there he goes, lightning speed. But eventually he runs out of the screen, and that stops the program, stops the loop, because his x and y coordinates are no longer between positive 300 and negative 300. Okay, so you get some really cool abstract art out of this, and I call it Etch-a-Sketch. And it's different every time because it's randomness, right? So I stayed up there longer this time, and so you can create some cool abstract art just with the turtle moving very quickly. So it's pretty fun. Any questions about this program, how it's working? See why that loop is eventually going to stop. That's a little fun one, I think. I next have a fun example that has to do with math. So this is going to be very interesting. Let me make a program that approximates the value of pi. So we all like pi, right? So it's a wonderful, wonderful idea. There's a really cool proof behind it, but the idea is like, if you were in real life and you had enough time, if you threw darts at a dartboard and counted, like let's say that you throw darts and here's your dartboard, it's circular, and then you draw a little square around it too, and let's say that you're such a good dart thrower that you only can ever, your darts are always within the square at least. You never hit the wall outside of the square. Your darts are always within the square. If you throw enough darts at this square, and some of them, of course, are going to land within the circle, some of them are going to land outside of the circle, you can approximate pi. It's so cool. The idea is, like, what if you threw darts randomly here? Some are going to land inside, some are going to land outside randomly, right? And so the probability that you threw a dart and it hit the center, it actually, like, it wasn't the outer part of the square, it was like the circle part. The probability that you hit that part, if you were throwing a dart randomly and had it could have gone there just as well as it could have gone anywhere else. The odds of you hitting that circle have to do with the ratio of areas of the circle to the area of the square. Does that make sense? And the area of a circle, let's say that this is just like a unit 1 circle. It's radius 1, it's like a 2 by 2 square that would have to cover it. The ratio of these areas is, well, this is pi times 1 squared, so it's pi for the circle over what's the area of the square? 4. So on average, like your dart is going to hit the middle of the circle, pi over 4 chance %. Isn't that interesting? So if you just keep track of, just like set a square, and you pick a bunch of random points in that square, I keep saying rectangle, in that square, to throw a dart, and you randomly do that, pick coordinates where your dart just landed, and you just count how many times that random dart hit inside the circle, and you divide by the number of darts that you threw, that approximates pi over 4. It's the ratio of those areas. If you throw enough darts, it becomes accurate. You have to throw way too many darts that you could never do this in real life, but we can do it in code. And so that gives you an approximation for pi over 4. And so if we just multiply whatever we get by 4, we get an approximation of pi. Isn't that cool? That's so crazy. And so let's say that this is like 0, 0 right here, 0, 0 right there. And we only allow our darts to be thrown within this range. So where is this? This is like positive 1 over here, negative 1 over there, isn't it? So I think we're going to throw some darts, and the x and y coordinates are going to be between negative 1 and positive 1. So import random. Well, let's say that we are going to throw total darts, many darts. So like 1,000,000 darts. 1,000,000 darts to throw. And then we're going to keep track of how many darts landed within the circle. This is so cool. It's very satisfying. Darts inside circle. If you like this, you can maybe do it, show it on a display with the Python turtle library. I think that would be helpful, but we're just going to do it in code only right now. No graphics. We're going to keep track of how many darts land within the circle. 0 to start, of course. And so we're going to throw total darts. I'll say like 4i in range, total darts. That will loop and run the body exactly total darts time. Okay, because range goes from like 0 to that thing minus 1. So it's that many things total, just starting at 0. We're just never going to use I. We're going to use I to just range for us. So I want to throw total darts, 1,000,000 darts. And each time I have a new dart, I want to throw a dart, figure out where it landed, and see if it landed in the circle. All right, so I'm going to throw a dart within this square. We're going to assume we can only hit within the square. What are the coordinates that bound this square? We got, this is positive 1, x, negative 1, x, positive 1, y, negative 1, y. So I'm going to, here's the x coordinate of my random dart throw. Random dot, it's uniform. Remember that one? Negative 1.0 to positive 1.0. That'll give me a random number with decimals. So it could be anywhere between negative 1 and positive 1. And then same for y. See how that'll give me a coordinate of somewhere in this dartboard, the square at least. Maybe it's in the circle too. And then we need to check and see if it landed in the circle. Okay? So, how do we check if this dart landed within the circle, like this one right here? How do we check if it landed within the circle? Well, we just want to measure, right? It landed within the circle if the distance from that dart to 0, 0 is less than 1, because the radius was 1. So it landed within the circle if it's there. It landed outside of the circle if if the distance between that is bigger than 1. You know it's bigger because it would have been a larger radius. It's not part of the circle at that point. Isn't that cool? So if you think about it long enough, you're going to do like the distance formula. It's like x1 minus x2 minus x1 squared plus y2 minus y1 squared. Then you take the square root of that. So it's just if, because the other one's like 0, 0, it's just if x squared plus y squared. Kind of like the equation of a circle, right? X squared plus y squared less than or equal to 1. That's your equation of a radius 1 circle. So if that's true about x and y, it was part of the circle. And we should increment the darts inside the circle variable, because another one landed within. Oops, that should be an equal. Equal that plus 1. And yeah, just let that happen 1,000,000 times. Just like throw a random dart. If it landed within the circle, we'll know it if this is true. It's less than the radius 1, the distance to the origin, and we'll just keep track of that. And so, all right, that ratio of the number of darts inside the circle to number of darts total, so darts inside a circle, over total darts, that approximates pi over 4. So if we multiply that by 4, that will approximate pi. Isn't that cool? And this is very inefficient, but the computer is pretty fast at it. It'll get it close enough to like 2 decimal places. You have to throw like billions, trillions of darts to get good accuracy, but we'll just throw 1,000,000 to start. So yeah, it went very quickly, and this was its approximation of pi. 3.14 had it correct to 2 decimal places. Isn't that fun? So if you want it to be more accurate, you throw more darts. So let's try throwing 10 million darts. It's going to take 10 times as long now to do the simulation, though. Slowly but surely. And this one is accurate to 3 decimal places. 3.1415, right? You round up to 2. So that's better. And so if you throw infinitely many darts, you will exactly approximate pi. But isn't that fun? The things you can do, you can simulate stuff with code. And so that's a good example of the random library and looping, I would say. Are there any questions about this program and how it's working? It's pretty fun. Let's see. Yeah, if we're good there. I just have a bunch of examples. Feel free to derail me at any point. This stuff is for you. Next, I would like to draw target logos. Eventually, we'll draw the real target logo. But let's start with a simpler version of that. Let's make a square Target logo. And this is me paying homage to Target because when I went to grad school at UCSB, there was not a Target for 5 of the 6 years that I went there. There was just a Kmart, and it was the second highest grossing Kmart in the country because there was nothing else around. It was horrible. And so eventually, my 5th year there, they made a Target, and I was just so happy. And so I'm dedicating part of this lecture to Target. So yeah, let's make a rectangular Target logo. And I think the best way to do it would be, just squares, of course, would be to make a draw square function that, like, what do you need to draw a square? Do you see if I drew a red square first, and then, like, it would be all red at that point. And then if I drew a smaller white square, that would, like, cut out part of the red square. And then I draw an even smaller red square on top of that. Like, if I did things in that order, I would get a Target logo. First a giant red square, then paint over the middle with a white square, and then paint over the middle of that with a smaller red square. See that? If I did that, I would get a Target logo. So let's make a function that kind of does all that. What do we need to draw a square? We need, like, the center of the square. So given the center of the square, like 0, 0, tell me the width of the square, like, I don't know, 200 by 200, and then also the color, because we're going to flip-flop it from white to red sometimes. That's like enough information to go and draw a square of a certain color at a certain spot. Yeah? Like, that's going to be the function that we're going to create, and apparently these 3 sizes are the right sizes. Size 200 first for the big red one, then 125 for the inner white one, and then 50 for the inner red one. That will work well. Okay? Let's do target square.pi. Okay. Do I have my other turtle program easily accessible? That would be nice to just steal that code right now. Etch-a-sketch. Yeah, let's steal some of this code here. Got to import the turtle library. We're not going to need randomness. The turtle doesn't have to go fast. We want to watch him work. So here is what we'll do. We'll make a draw square function. A function that draws a square of a given center point, a width, and a color. And then once we have that, we're going to draw first a size 200 square. We're going to call our function draw square. This is just a function that does something. It's meant to be called in a line by itself. Center should always be 0, 0, probably, just like we'll center the target logo. Let's do size 200 to start, and then that should be colored red. That's the outermost square, size 200. And then we're going to draw 2 more squares, inner squares. The next one's going to be of size 125, and it'll be white. And then the innermost one will be of size 50, and it'll be red again. So you see how if I had that draw square function, I could just call it 3 times, and it would give me my pretty picture. So that's what I want. And so given this information, let's go and draw a square. How do we do it? How do we calculate this? Let's figure it out together. Let's see here. What in the world? Something's off a little bit in my notes here. Let me try to fix them. Let's go to a different set of them. Sorry, technical difficulties. Let's do that one. That should work. That's back to normal. Okay, so I got those 3 things. That would be nice. Dun, dun, dun. So here's kind of what I want. So like, given the center point, how do I figure out like where this logo should be drawn? Given 0, 0, this is my center point. It's like my center X and center Y. I can get those out. I can say, I can get the center X and center Y out of center. Or do I want to say that? Like center X. Because it's a tuple, right? Center is a big thing. 2 things, like a list. The X part of center is the 0th thing. Center at index 0. And then the Y coordinate would be at index 1. Okay? So I have those. And then how do I draw like a square of that size? We know how to draw a square if we have the corners, right? We need to get to the corners. So if this is a 200 by 200 square, this is 125, this is 50, and we're drawing this outermost one, so we're sitting at 0, 0. How do we get to like this starting coordinate? Because we know like the upper left. That's what we care about. How do we figure out the coordinates of that upper left? Well, if we know its side length is 200 and we're in the middle, we have the coordinates for the middle, we could just go left by half the size, 100, and then also up by half the size, another 100. And that would put us in a spot where we know how to draw a square, right? So how do we calculate from our starting center X and center Y? What is the upper left corner of that square? It's going to be center, the original center X. So what's the X coordinate? It's going to be the original center X, and then we have to move left by 100. So minus 100, or half of your width. It's called width. Minus width over 2. You see how that'll give you the X coordinate? And then the same thing for the Y. Starting at center Y, how do we get to the Y coordinate of this bit? We want to go up, right? We want to go up by 100. So it's going to be center Y. Starting here, go up by 100. That's in the positive Y direction. So plus width over 2. See that? That'll get us the upper left corner of that logo there. That's pretty nice. So, yeah, I think that's enough. And then we can all right, now face right, do your turns. We know how to go forward by the size and all that. So that should work. So let's make that happen. So I know that my upper left coordinate of my square is center X minus width over 2, comma, center Y plus width over 2. That'll be nice. And then I want to go there. Tell the turtle to go there. Turtle dot up to pick his tail up so it doesn't make a mark as he goes there. Turtle dot go to UL. Just give it the coordinates. And now set your tail back down. We're ready to make marks. And then if we're up here in the top left, we want to set our heading to face east so that we're ready to go forward and to the right. So turtle dot set heading of 0 there. That'll get him facing right. And yeah, let's just draw a square right now. We'll eventually deal with color after that. Let's just get this working first. So it's turtle dot forward by whatever the width was. Yeah, that'll draw the top part. And we want to turn right 90. Turtle dot right 90 degrees. And then we're going to go forward by width again and turn right again. So we'll just repeat this. You can put it in a loop if you wanted to, I guess. There's no need to turn right at the end again. But as long as you go forward width and you keep on turning right each time, you'll eventually end up drawing a square. And so that is us using center and width to get our squares drawn. Right now they don't have any color though. But there are our squares. Any questions about why the function is doing this so far? because the last piece of the puzzle is just to fill it in. So the way you do that is the begin fill and end fill. You remember that? So if you wrap your draw shape in turtle.begin fill and turtle.end fill, that tells the turtle, I want to fill with my fill color, end fill. Fill that shape with my current fill color. And we're getting told every time this function gets called what color we want to fill this shape in with. So we want to set our fill color. It's turtle.fillColor to be whatever that color was. Maybe it was red, maybe it was white. You could make some weird target logo with different colors if you wanted to. But that is what we need there. Okay, does that make sense? That'll always set the fill color right in time before we start drawing stuff. And so red, white, red again. Cool. It's a little jagged due to just the way the turtle gets drawn. If you make the window bigger, it stops being jagged for me. That's funny. But yeah, there's your rectangular target logo using functions to save the day, making our lives much easier. Any questions about that? That's pretty cool. So, let us do the real target logo now. We'll take what we had and we'll make it better. Let's make a circular target logo. And this is going to be interesting as well, because when you draw circles with the turtle, you need to be at the bottom, surprisingly. You say turtle.circle, and let's see. Am I doing this right? And then you give like the, what is it? You give the radius that you want to draw the circle of. And where actually is that definition? Turtle.circle. Let's go up to the top. Circle, please. I don't want to search there. There it is. Circle. And you give the radius of that circle. So turtle.circle of radius 50. And the weird thing about the turtle is he starts drawing the circle straight up. Like if you want him to draw this exact red circle, the outermost one, the turtle needs to be placed right here. We tell him, I want a radius 200 circle or whatever. That's the idea. Okay, so that's what we need. We need to, we're given the center point again. We had our function that gave us the center point. We need to move the turtle down here. Like go in the negative y direction by width over 2. Does that make sense? Just to get us down here. This is like our same center x that we were given, but the center y, we need to move down to here to draw a circle. Because the turtle will move in this way. You got to be at the bottom point of it. Center y minus width over 2. That's what we need there. So let's do that for circles, and then maybe we'll make a triangle one too. So I'll copy all this code. I'll say, what should I call it? We'll call it target improved.py, making a better version of it. So we'll keep all our same stuff. We'll just not use the draw square this time. Instead of draw square, do you see how, instead of this, if we did draw circle, that would work? We just had a bunch of draw circle functions that worked similarly. We would draw a circular target logo, yeah? So let's take this, and I'm going to comment out these lines so that they don't have any effect anymore. They're just comments now. They're not real code. But now we'll do the draw circle, okay? We'll do the draw circle, and we'll make it very similar to draw square. So if I only had a draw circle function, I could do this. I could make a circular target logo. So that's pretty nice. It's very similar to what I already had. So if only I had a draw circle function, and how can we implement that? So it's always center point, width of the circle, and what color we want to draw it. So it's not called the upper left anymore. It's like the center of the circle. It's or the bottom part. It's just where we want to start drawing. Let's just call it starting point. It is center x. Keep the same one. Just move down in the y direction. Get the very bottom middle bit of the circle, because that's apparently how the turtle needs to draw its circles. Still get there. We don't have to mess with the heading anymore. That's really not necessary. I think it is. Face right. Keep them facing right, so that it'll draw it to the right. and go up. And then, yeah, set the fill color, and then in between begin and end fill, we want to draw a circle. We say turtle dot circle. And when we passed this 200, 125, 50, it was meant to be the width of the circle. And so the turtle dot circle function takes the radius. The width of a circle is its diameter, and so the radius is half of that, width over 2. So that'll draw the circle of that size, all right, of that radius length. So it's really a radius 100 circle, the big one that's red. Yeah, that's how we'll do that. So, oops. Oh, I forgot to rename it. I have 2 draw squares right now. This new one, this copied one, should be called draw a circle. Oh, what did I do wrong again? Oh, see, Python's very helpful. I copied too much still. It's not go to UL anymore. We changed UL. We're calling it starting point. That's a better idea. Better name for that. So yeah, just follow the errors and eventually you'll make it work. And so there is a red circle, a white circle, and a red circle. So we have the real target logo now. Isn't it beautiful? Any questions about that? Does that make enough sense? Let's see. A little bit out of order because, like, okay, cool. We can draw in exactly the same way. We can draw a circular target logo and a square target logo. We can keep going with this pattern, right? We can draw triangular target logos. Why not? We can totally do that by making like a draw triangle function. We made a draw square. We made a draw circle. We can just make a draw triangle function and use that. Won't that work? That'll be nice. So the way we get there is we say we'll draw an equilateral triangle, and apparently if we give the center point of our triangle, this is a little weird, but the way to get to the bottom left, because that's where we start drawing our triangles usually, the way to get to the bottom left of a triangle is you move down by not like half of the height of the triangle, half of the width of the triangle or whatever, of the side length. It is a third. You move down by a third of the width. That's just a weird quirk of how triangles work. Equilateral triangles, you move down by a third, and then you go over by half of the side length, half of that width. So the bottom left is center x, go left by width over 2, and then go down center y minus width over 3. It's very odd, but that's just how the math checks out. But we can use that to draw a triangular target logo, and I think it's easier to copy draw square to make that happen, to make a draw triangle function of a given center point, width, and color. So it's not UL anymore. It's like BL. It's bottom left, where we're going to start drawing the triangle. That's where we did it last time. And that's going to be equal to center x minus width over 2, and then center y minus width over 3, which is very weird. Where width is like the side length of your triangle. Remember that the height is not going to be the same as the side length for this triangle, but at least it'll be centered properly if we do it this way. And now we're going to go to BL. I won't do that again. And then we're going to face right. And so we're going to draw the bottom part of the triangle, go forward with, and it's not right 90. It's going to be like turn left. You remember the deal with these equilateral triangles? It's like a 60 degrees right here. So if we're facing this way, we want to turn left by 180 minus 60. Remember that? So turn left by 120, which we can just let Python do it, 180 minus 60. Okay, so that is what we want to do a bunch of times instead of right. Not right, but left. And then go forward by the width. And there are only 3 sides of a triangle, so you only have to go forward 3 times. There. I believe that is a draw triangle function. We'll call it what it is. Oops, triangle, center. And so you see how I was just easily able to change the draw square to a draw triangle. We still have a center point. We're going to start in the bottom left. That's that one. We're going to go there, set the fill color, and like here's how you draw an equilateral triangle. Go forward by your width 3 times and turn left by that amount. Yeah. And again, it's the same pattern. This is really powerful and cool. If I take this, is there a way to comment out things easily? Oh yeah, nice. No, I don't like the way it does it though. Never mind. So instead of saying draw a circle, all these things, we can say draw a triangle this time. And I'll again comment out these lines so that they don't have any effect. And somehow I've lost my pretty colors. Now it's not drawing it with red. So I'm just going to close that and open it again. Now I have my colors back. That was weird. Yeah, do you see how it's exactly the same? Instead of draw a circle this time 3 times, we'll just say draw a triangle 3 times. And that will draw a triangular target logo, thanks to our draw triangle function. Cool. So yeah, I think that is as far as I want to go in that direction. Does that make sense? Like, isn't that cool? Like, we can just like do the same thing with a bunch of different functions, and it'll all work the same. Any questions about that? We learned how to draw a bunch of shapes right now. But I claim that we can go further than this. We can make it better, because this is just a lot of repeated work. Do you see how like drawing a target logo involves drawing things of this exact size, with these exact colors, with the same center point? We can generalize over that, can't we? We can make, instead of like calling draw circle 3 times, drawing square 3 times, we can make a draw target logo function. Does that make sense? And then we can give like how we want to make it drawn, how, like, give it center point, give how we want to make the shapes. Do we want to make triangles? Do we want to make squares? Do we want to make circles out of it? So what we're going to do is we're going to make a draw target logo function that takes one of our shape drawing functions as an argument. You can have functions that take other functions as arguments and used as parameters. So that's pretty cool. So let's comment all of this out, and let me show you the magic of functions if you are not, if you haven't seen the light yet. So here's kind of what I want to do. Instead of all of this, because we see that there's a pattern going on here, let's generalize over that pattern. We'll say def draw target logo. Let's make a draw target logo function. Because all you need to draw a target logo is tell me where its center point is, and then give me the kind of function that draws the shape, right? Give me a draw shape function. And you see, if I just called that, I would make a circular target logo very easily. I could be like draw a target logo using, I don't know, 0 as the center, and use draw circle as my shape drawing function. Like, I'm passing a function to a function. Isn't that cool? And up here, it's being passed and it's being called draw shape. So instead of saying draw circle 3 times at that particular thing, we're going to say draw shape. Whatever shape drawing function was passed to us, that's the one I want to use to draw this logo. Boop. Draw shape, draw shape, draw shape. If I pass along draw circle, that's what draw shape is right now. And then the center point is also being given to us. So instead of 0, 0, we're not going to hard code it anymore. We're going to make it whatever the center point the user wanted me to give it as. And so now, once I have this at my fingertips, I can make any kind of shaped target logo with 1 line rather than 3. Isn't that cool? I'm making a draw target logo function that takes my circle drawing function as its second argument. And it's working. That's really powerful and cool. Are there any questions about why that works? Like, it's just another name, like it's just a function, right? Just pass it along into something of some other name and you can call it. If it's a function, it's able to be called. So draw a circle for the time that this function is running, it's called draw shape. Because we're passing along into here. It's just another argument. That's pretty cool. And so now, I guess, let's draw them all. Let's draw target logo 3 times. One with draw circle, one with draw square, and one with draw triangle. Different kinds of target logos. Let's not have them be on top of each other. Let's be like, this one can be up and to the right, 150, 150. The square target logo. The circular target logo can be down and to the left, negative 150. Negative 150 can be at center. And then the triangle one can be in the middle. Okay? And so again, I'm just piggybacking on top of all this work that I've done. This draw square, draw circle, draw triangle function. We noticed a pattern. We made a function to take advantage of that pattern. And like, with a single line, we can draw a target logo of a given kind of shape. That's so cool. So square draw target logo. We're passing along draw square into draw shape. And like every time we call draw shape, it becomes draw square. And if we pass along draw circle into draw shape, now every time we call it, it's drawing circles. And same for draw triangle. And so just like with 3 3 nice lines at the end. We can draw our target logos of any kind of shape by passing along a different shape drawing function. And that is very satisfying to me, at least. Are there any questions about that? That's a fun one to study for sure. I hate that the square is jagged. You just have to like resize the window until it goes away. Sometimes it doesn't. So sad. But yeah, it's very pretty, very satisfying. And that is a good example of using functions and like noticing a pattern and making another function to take advantage of that pattern. Make your life easier. Less code for you. All right. So if we are happy with that, that's pretty much all I've got. I just want to show you next some cool examples that I didn't have time to get to in lecture, just to show you the full extent of like what you can do with just the turtle library. Like once you learn more programming, you can make some really cool looking stuff, and I'll show you an example of that. So let me copy in 2 files to our code from class. Let me go, here's our stuff from today. I'm going to copy it in from a previous semester. We'll go to F23, I guess, was the last time I taught this class, right? And then I have 2 cool programs with these names. So the first one is you can make a program that draws this kind of abstract art. You know, the person who made this, his name was Pete Mondrian, right? And so you can make this using functions, just with enough functions, with enough thought, you can like identify what it means to make this kind of stuff. Because it's really just a bunch of lines, right? It's a bunch of lines, and like between some lines, you're drawing colors, essentially. So kind of here's how I thought about it. Here's the algorithm. Let me just show you it working at first, maybe. Let's see, this is this semester. This is not this semester. So here is, let's edit with idle. Here's the program. I'm doing a bunch of stuff. I have a draw rectangle function. I have a draw line function. I have a pick a random color function. And then just a bunch of loops and stuff. And eventually here's how it works. It picks a bunch of like lines and it starts drawing those lines. And then I tell the turtle to like let me have control. And I'll just keep pressing enter. And it's going to pick some spots to draw things. And eventually, when I'm happy with the result, I can stop the program and have my pretty artwork. It's really not picking yellow very often right now, is it? Whee! But yeah, when you're happy enough, eventually, you can say Q. It's like, all right, I'm done now. Yeah, Q. Okay, now I think it's finished. But that was a bad example. Let me rerun it. It's all random. So pick some places, and actually just for fun, let's do it one more time. I like those better. 2, 3, 4, 5. I'll say Q now, and then like draws the bounds. And so I've got some cool abstract art in that same style. So it's different every time, but here's kind of how I thought about the program. You'll eventually learn how to break this kind of stuff down. Like I noticed, okay, really, this artwork is based on a bunch of lines, a bunch of horizontal lines and a bunch of vertical lines. And I said those backwards. And essentially, like what you want to do to make this work is like pick a bunch of those, draw them, draw a bunch of horizontal lines and a bunch of vertical lines, draw them all, and then repeatedly pick like 2 horizontal lines and 2 vertical lines. Like pick this line and this line and this line and this line. Do you see how those like combine to make this square bit right there? Like that is a place that you could start drawing. Like figure out the bounds, draw a square or some rectangle, right? It's not really always a square. Draw a rectangle there of a random color. Does that make sense? You could program that. I believe that you could. It's like, all right, those form a rectangle, those bounds, and then fill that in with one of those colors that was used in the artwork. And then finally at the very end, I crop off the edges. But you can kind of see that working. Like here I am, like setting the drawing's bounds, picking 6 vertical lines, 8 horizontal lines, because that's apparently how many there was in the original painting. Drawing them, I have my draw line function, And then forever, I'm asking the user how many times they want to fill in a random spot there with a rectangle that's colored randomly. But yeah, I'm picking, like, figuring out where the rectangle should be drawn, picking those random lines, and filling it in, and eventually I'm cropping off the image by drawing white lines around the edges. So yeah, that, with enough randomness, enough of you pressing enter a few times, and then Q, will lead to cool looking artwork. Isn't that beautiful? So yeah, you can make it more precise, but like that's an example program that you could do. I hope that makes sense, and that'll be fun for you to look at maybe and make your own. And then I also have an example for this this little album cover. Does everybody know, like, have we seen people, like, all the hipsters wear this shirt with the Joy Division album on it? Like, apparently, this artwork, we can recreate it very easily. I've made a program for that as well. You can recreate that image with the turtle library. This one's much more complicated because apparently these wavy lines are public domain knowledge. It's from this thing. So the album itself, this artwork, comes from somebody's, like, PhD thesis, I think, where they took some readings from a pulsar, some celestial object that emits radio waves, and they took a bunch of readings of a bunch of its pulses, and they read and they graphed them out in a pretty way. And so apparently back in, let's see, they discovered the thing in 1967, but I think the reading was taken later. And, like, it ended up on the cover of an album, which is kind of cool to think about. And so, yeah, all we need to know is these, like, what are these signals? Like, remember the signals for the radio waves? Here they are. It's just a list of lists. You can put lists within lists, why not? Like, here's the first pulse. It started with this much intensity, then the next time they took a reading, it was this much intensity. And so you see, like, it's going down, then it's going up. Then it's going up, then it's going down again. If you just have the turtle move up and down and left and right a little bit as it's doing it, you'll draw these wavy lines. It's like those are the readings. That's pretty cool. And so let me run it while it's doing all that. So here it is. It's drawing the image. We'll get there in a second. But, like, it's going through all these signals and it's doing some fun stuff. I will not take the time to say this. I'm making the turtle draw stuff really quickly. I have a draw rectangle function again. And it's actually a draw polygon function that I really need. If you think about it, like, the front stuff needs to block off the back stuff. And so really it's not just white lines that you draw. It's really you're filling in those lines at the bottom there. It's like the next line, it's overwriting the previous one. So it's really like black all the way to the bottom. That's what you're filling in. It's like really a filled-in polygon. Looks a little weird. And we're drawing lines, and I call them fuzzy lines. And so it's just looping through all those readings up there, and, like, going up, like moving the turtle right every time, and going up if the signal goes up, and going down if the signal goes down. And yeah, it's just a bunch of functions and loops. With enough practice and enough thought, you can make this happen. And so eventually, this will get finished. The turtle is working very hard right now, and it does take a lot of time, but he's eventually done. And this looks exactly like this, because it is. It's the same reading, and you can recreate that with code. With enough functions, with enough loops, you can do whatever you need. And that is the power of computer science. And also, just for a fun takeaway, like, in addition to the cool artwork, you get a tiny turtle at the bottom right. So that makes it even better. So yeah, that's, like, the coolest example that I can show you, hopefully, to convince you that, like, programming is something people care about, and it's useful to know. But yeah, I would never test you on this kind of program. It's a very complicated one. I just wanted to show you the extent that you could go to. Okay, so feel free. I'll give you the code if you want to look at it. Feel free to look at it. But I think that's all that I wanted to say. Are there any questions about any of the programming stuff that we were talking about today? So yeah, if we're happy, that is the end. We made it to the last lecture, the end of the class. So all that I can say now is thank you for, like, putting up with me. And then also, if you have not yet drunk the Kool-Aid of computer science, kind of the purpose of this class is to convince you to become a computer science major, to get more people in the major. And so if you like what you saw, especially in the programming portion of this class, definitely consider becoming a computer science major or something that's closely related. That is me trying to convince you. So yeah, thank you for your patience and putting up with me. All that we have left after this is the final, which will be on Monday at the same time as class. Don't forget, it'll be here. You'll come and you'll take it at one of these computers, or you can bring your laptop, take it on that. And like this will be available. Just click it, just like the midterm, and start taking it. The time will start ticking down just as usual.
Is that like open note and stuff?
Yeah. Everything is on the final info page, open book and open notes, just like the midterm. So yeah, I think that's all that I wanted to say and record. The rest of the time is yours to ask me questions or